tunnel field effect transistor have emerged as leading contenders to outperform conventional MOS-based devices for low-power applications. Tunnel FET can be a replacement to conventional silicon-on-insulator-based MOS devices for steep switching applications, but can it also serve as a substitute to MOS-based capacitorless dynamic memory? So, we aim at exploring tunnel FET-based dynamic memory. The conventional MOS devices utilizes the P-type body to serve as potential well for charge storage, while tunnel FET, having P+In+ structure, has no well formation. So, the first concern is formation of potential well for charge storage. The problem was circumvented by the use of an asymmetric fully depleted double-gate silicon-on-insulator tunnel FET as dynamic memory. The design utilized a front gate of 400 nanometers, partially covering the intrinsic region, while the back gate covered the complete intrinsic region. The back gate creates a potential well at the underlap region of 200 nanometers. Although, the previously proposed topology paved a way forward for tunnel FET-based dynamic memory, the characteristics obtained were not competitive to outperform the previous work on capacitor-less dynamic memory. Previous work on tunnel FET-based dynamic memory showed retention time in few milliseconds at room temperature. The retention time achieved was lower than the target of 64 milliseconds and hence, required improvement. Our work focuses on enhancing the retention characteristics, achieved through design optimization in 3 steps. Incorporation of these steps increases the retention time from 80 milliseconds to 550 milliseconds at 85 degrees Celsius. The question is, how is it possible? Step 1. Use of a misaligned double-gate tunnel field effect transistor. The architecture utilizes a front and back gate length of 100 nanometer. During fabrication, back gate misalignment is possible through shifting of electric vernier. Next, we focus on significance of back gate alignment, work function and bias to operate tunnel FET as dynamic memory. Misaligned backgate creates a deeper potential well that sustain charges for longer duration. This is better than the design with backgate at complete intrinsic region that shows a shallower potential well. N+ poly front gate governs the read mechanism based on band-to-band tunneling, while P+ poly back gate creates a deep storage region. Retention characteristics are governed by recombination and generation phenomenon that can be regulated by bias applied. Therefore, optimal bias aid longer sustenance of charges that result into increased retention time. Thus, appropriate backgate alignment, work function and bias results into deep potential well. That increases retention time to 80 milliseconds at 85 degrees Celsius. Now, we progress a step forward to further improve the retention characteristics. Step 2, use of a lateral space, or gap between the gates. It increases the effective length of storage region, and thus, retention time increases to 250 milliseconds. Hence, retention time increases from 80 milliseconds from step 1 to 250 milliseconds. Is further enhancement in retention time possible? Yes, this is possible through step 3. That uses an underlap between backgate and drain. The underlap reduces the band-to-band tunneling of electron, thereby decreasing the hole generation in the potential well. This reduces the state zero degradation, thereby enhancing the retention time to 550 milliseconds at 85 degrees Celsius. The incorporation of all the 3 steps not only improve retention characteristics but also the scalability of the storage region. Incorporation of lateral space and underlap allows the storage region to be scaled down to 25 nanometer with retention time still higher than 64 milliseconds with the front gate region of 100 nanometer. Thus, The design optimization result into improved scalability and enhanced retention characteristics, which is much better than previous proposed methods on tunnel fit-based dynamic memory.